Today I am just going to start with talking about the Big Bang Theory and reviewing some of the concepts that you guys were sent last week through videos, and just kind of talk about how this whole thing came about. So first of all, let's just make sure that we understand a little bit of vocabulary. Sometimes students get confused between rotate and revolve, and the easiest way that I can think about this is just remembering what's happening with the Earth and the Sun. So rotate means something spins or turns on its axes. The Earth rotates, the Moon rotates. It takes 24 hours for the Earth to rotate, and that's one day. So we get day and night. Revolve means go around or orbit. So it takes 365 days for us to revolve around the sun. That's a year. All right, just something to remember. And because of this revolution, we get different seasons, more specifically winter and summer. For the next few minutes, I would love it if you would write down everything in yellow. One of the great things about these videos is that you can pause, write down what you need to, and then continue on. So first of all, the universe, everything that exists in any place, all the space, matter, energy, and existence. And you've seen this in your videos, but they're approximating the universe is about 13.7 billion years old. And we'll talk about some pieces of evidence that correspond with that age. Celestial objects, any object outside or above Earth's atmosphere. A celestial object could be a planet, or a star, or a galaxy, or a meteorite, or a dwarf planet. So anything outside or above Earth's atmosphere. You can see over 6,000 celestial objects with your very own eyes just from Earth. So when we talk about the Big Bang Theory, we're talking about the way the universe was formed. And according to the theory, all matter and energy started out of a concentrated, very small area, and a huge expansion happened. It's important to realize that a lot of people think that the Big Bang was an explosion, but it's not an explosion, it's an expansion. And then from there, matter began to organize into atoms. So let's talk about how this occurred. So about 13.7 billion years ago, the universe begins. It's the size of a single atom. There was a violent expansion, and then all matter and space was created from this single point of pure energy in an instant. Didn't take very long, but approximately 3 minutes after this violent expansion, it's growing from the size of an atom to a grapefruit. And this was all, of course, it was all collaborated with Einstein's E equals mc squared. So it says if you have a very tiny amount of mass, it can hold tremendous amounts of energy. So they're saying that energy then froze into matter, and then it started clumping up. So those clumps today are called protons, neutrons, and electrons. And they're going to come into play a little bit later. But all those parts formed our atoms, which creates our elements, which creates us. You know, we're primarily carbon and nitrogen and oxygen. So thank goodness that all this energy did turn into clumps, because here we are. It takes several hundred thousands of years, though, for those atoms to start creating things like hydrogen and helium. And even today, our atmosphere is a large portion of it is hydrogen. So this early universe was about 75% hydrogen and 25% helium. 200 to 400 million years after the Big Bang, we're getting our stars and our galaxies. And then 4.6 billion years ago, we get our solar system forms. It's important to remember that when we're talking about a scientific theory, this is something that is a well-substantiated explanation. When you're talking about a theory in science, it means it has gone through repeated tests and observations and experimentation. This is not something that somebody just pulled out of the air and said, this is how it happened. This is a substantiated explanation. Whereas when you're talking about an assumption, that is something that is accepted without evidence. A scientific theory is based on evidence. So what I'm going to do is I'm just going to briefly go through the 6 pieces of evidence that have corroborated the Big Bang Theory. The first one, and probably the most important one, is the universal expansion and Hubble's Law. And you watch the video on the Doppler Effect and on Redshift, and that's basically what this is talking about. It says Hubble observed that the majority of galaxies were moving away from us. The further they are, the faster they're moving. And this is because when we're talking about light waves come in different colors, and we can see these things. And so if you have an object where their frequency is shifting towards the red spectrum, they're moving away from us. If their frequencies are moving towards us, then they're more on that blue spectrum. So redshift was a really important observation to make and to show that basically almost everything is moving away from us. The redshift of light discovered by Hubble shows that light emitted from stars is shifted to the red part of the spectrum. It's also called the Doppler Effect. So again, if you look at some of these lines, you can look at the one on the lower right in the middle. It says that's the spectrum at rest. So notice those 2 little lines in the middle. And if that object was moving towards us, those 2 little lines would be shifting towards the blue. If they're moving away from us, those 2 little lines are shifting towards the red. And of course, here you just have a couple of different examples of here's the sodium lines, and then where they shifted to the red, and then where they shift to the blue. So one of the easy ones, because there is so much hydrogen in the universe and there's so much hydrogen here in our atmosphere, is that it's just one of those gases that has a really unique fingerprint. And if you look down there, you can see that it has a very large red wavelength. So we're going to use hydrogen to look at various galaxies. Here's the Orion Nebula. It's made mostly of hydrogen. It's really not that far away from us. It has a lot of oxygen as well, which is why you see those green lines on the spectrum. Here's another galaxy. It's a little bit further away. It has a lot of hydrogen as well, but if you look at where the location of the 656 hydrogen line is, you can see that hydrogen line has shifted to the red. Another galaxy even more further away, you can see that that hydrogen line is shifting towards the red. Here's another galaxy. So the greater the redshift, the faster that galaxy is receding. And here on this galaxy, it's receding so fast that note that that hydrogen line has even shifted all the way past the red, and it's now in the infrared region of the spectrum. And again, an even further galaxy, and you can see it's almost past the infrared. So all of this is just based on the Doppler effect, which you got in your video last week, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. If it's moving towards us, it has a shorter wavelength, so that's blue. If it's moving away from us, it has a longer wavelength, and that's red. The second form of evidence for the Big Bang is this thing called background radiation. So this noise radiation, the static that's evenly spread across space. And if you think back to the law of conservation of energy, energy can neither be created or destroyed. That energy still remains out there, constant over time. So we have this satellite, it's called the COBE, and it confirmed that the entire universe has an even noise radiation that's spread everywhere. The third evidence is something called quasars, these really super large galactic cores, puts out tons of light. These guys are only found 10 to 15 billion light years away, nowhere else. We have telescopes that could see past them, but we can't see anything past them. So maybe these guys are remnants from that possible Big Bang. For radioactive decay, we can actually date objects. We can use radiometric dating to see how much of a particular atom is still left in a material. And by knowing this, we can actually estimate Earth's formation. We can estimate the moon's formation. So pretty cool stuff. Stellar formation, we're going to be talking about how there are life cycles. Stars are born, they change into different kinds of stars, and then they go through a different process. So we can view these stars and they form, they burn, they explode. Things are changing out there. And then of course the speed of light and stellar distances. The speed of light is a universal constant. It's in Einstein's equation, E equals mc squared. C squared is the speed of light. It's a huge number, 300,000 kilometers per second squared. And we observe stars millions or even billions of light years away. A light year is just the distance that light travels in 1 year. And so the light we see today from a star 500 light years away is 500 years old. We can see the light of a star still, and we might not even know that that star burned out. Like, we're still seeing the light. It's pretty cool. The furthest stars away are 10 to 15 billion light years away. We can't see anything further. There's nothing else viewable past them, which means there must have been a beginning. And so if there is a beginning, there's an end. But here, what came first, the chicken or the egg? I don't know. How did we become who we are? How were we created into humans? It's just one of those constant questions that everybody thinks of. So I love astronomy. I hope you guys stick with me. Just write down your notes and mark that you finished this assignment. Thanks a lot, guys. Have a good day.